Everyone, it's August the 6th. Alright, yesterday was a good learning experience. It's always good practicing a segment tree. Alright, let's see what we have today. Alright, we're going to set a time limit. Again, 15 minutes. If nothing comes out of it, we are going to check the answer. Alright, game of dungeon consists of n by n rooms arranged in a grid. You're given 2D array fruits of size n by n, where fruit ij represents the number of fruit in the room rij. 3 children will play in the game dungeon with initial positions at the corner rooms 0, 0, 0, n-1, and n-1, 0. The children will make exactly n-1 moves according to the following rules to reach the bottom right corner. n-1 moves. n-1 moves. It's n by n room. A child starting from 0, 0 must move from their current room to one of the rooms. So I plus 1, j plus 1. So it's a diagonal and go down or go right if the target room exists. Child from 0 n-1, the top right corner, must move from the current room to one of I plus 1 j minus. So it's a diagonal to the left. This is a diagonal to the right. This is a diagonal to the left. This is the same, which is to go down. This is diagonal to the right. Wait, hold on. We should just kind of. So for this kid, we can go this direction, this direction, or this direction. For this one, we can go down. This has diagonal. Or this direction. So I plus 1, j plus 1. I plus 1, j minus 1. I plus 1, j. And for this kid, you can move I minus 1, j plus 1. So this direction. I, j plus 1 this direction. And this direction. Okay. When a child enters a room, they will collect all the fruits there. If 2 or more children enter the same room, only one child will collect the fruits, and the room will be emptied after they leave. Only one child. Return the maximum number of fruits the children can collect from the dungeon. First child moves 0, 0 to 1, 1. To 2, 2. To 3, 3. And you have to move n-1 to reach basically every time you move, because you need to reach here, the diagonal is exactly for this. So like if I deviate from diagonal, if I go here, so we have to move 3 steps, right? 1, 2, I cannot reach it for this. Is there any other way to reach if I don't go diagonal? I think for child 1, the only way is to go diagonal. It's like, how can we do 3 steps Right, so this is the fastest. If we deviate, then there's no way. Like, I cannot go back because that's wasted. So I think this can only go this way, right? Yeah, I think so. So this child can only go this way. So if we want to maximize, so the other children shouldn't touch this. For here, 1, 2, 3, we can go this way, or we can go. We can go this. So 1, 2, 3, 1, 2, 3, 1, 2, 3. 2. So I cannot deviate too much. I think if you deviate above 2, then you're going to be in trouble. Like, you stay this, it's fine. We can go here, it's also fine because we allow this, like, you can go this way, but you're also moving to the right. Basically, for here, every step has to move to the right. Right? Every step you have to move to the right, which is exactly true. Every step you move to the right, but at the same time, you cannot, because you cannot cause extra step to move too high up. Right? You cannot move too high up. If you move too high up, then you'll need an extra step to go down. So that is not going to work. So basically, you can go down, up and down, or up, staying on this row or staying on this row. Both are fine. So the same will apply to here as well. Okay. So with these constraints, I'll do this one first, and then we set everywhere to 0. Okay. Now is the real thing. So this and this. Now technically, they can overlap towards the end, because for this one, so this one, it's we see, yeah, it will not reach. So the only one that can be overlapping is this one. This is the only one that can be overlapping. However, this one's already taken, which means these two children should not overlap. They will never overlap. Right? So now we are facing, and also this one doesn't exist, right? So basically, a question is, for this child, we have these two rows, and we have things at 0. So we need to find the path that takes the largest value. And Dijkstra, can we use Dijkstra to do this? Yeah, this is just like we want to maximize as we go through. So we use Dijkstra to go through this, right? We use Dijkstra to go through this. So this will give us the maximum for this, right? When we reach to the end. And we'll go Dijkstra on this. So 2 rounds of Dijkstra, and yeah, we can try this one more time. So make sure that everything is correct. So this is all this. So we're gonna take this for sure, and then just 0, and then this is only one way. So it's 1, 2, 3, 4. Okay, let's try. So basically, have to write. I think that's what's needed. With the current advancement in AI, I feel like all these, what I'm doing is really just a hobby. I feel if you put this in the LLM, it can give you the answer really fast. All right, so since there is a hard restriction of moving n-1 steps to reach cell n-1, the child at 0, 0 only has one path going diagonal. Similarly, the child at n-1, 0 can only access cells on row n-2 and n-1. The child at 0, n-1 can only access cells on column n-2 and n-1. There is also no chance of overlap for not child 0, child 1. Okay, so child 0. I believe this is child 1. No, I'll call child 1. This is child 2. So I say there's also no chance of overlap for child 1 and 2 because the only cell that they can potentially meet is n-2, n-2, which has already been taken by child 0. So this problem is converted to finding the path that maximizes the number of fruits for child 1 and child 2 after child 0 has already taken its price, has already taken their fruits. 2 rounds of Dijkstra might work. Not sure, right? We're not sure, but we're gonna try. So for Dijkstra, what do you need? I definitely need the fruits, right? I need the fruit so that I know where things are. And we also need in the path, we need the next step, right? Next step. Basically is like what is the next move, so I can go through. Okay, those are the next moves. Okay, yeah. Okay, we can do that. So the next moves, and then we'll go through those. I have to remind myself how to write Dijkstra, but let's write Dijkstra first. Okay, so we do. So what do we need? Dijkstra. Dijkstra is the starting point, right? I, J, these are the starting point, and then we need the fruits, right? And we also need vector and the pair. What do we call this? We call this moves. No, DIDJ. That's what they are. Oh, direction. I don't remember what I call them. DIRs. Okay, so we need a. Oh Lord. I want a priority queue, a max heap. What is it max heap? Max heap of pair int and then pair int. A max heap storing type can be implemented using priority queue. By default, it is a max heap with highest priority determined by this. Structures like this, the default comparators is lexicographically compares first element of the outer. So we don't have to define our own. This is good enough. Oh, okay, that's actually good to know. So we need that. We also need. What do we also need? We need the maximum fruits. Now, for maximum fruit, we can just create a vector of only 2 rows, but I feel that actually might get things more complicated than I need to. So I am going to just, be lazy of creating the entire thing. Alright, so I'm going to say max fruits. Right, so it's going to be n, and this is going to be n as well. Right, so this is max fruits. We need that, and we need priority queue, which I just learned is a max heap. I actually know it's a max heap before, but it has to be this and std pair again. Alright, so that's gonna be max heap. Okay, so what do we do now? We put the starting position. Okay, so we have a starting position. The starting position has a fruit as well. So we put a starting position fruit into it, right? And then, actually, no, it's not a starting position. We are dealing with edges. It's like this edge has 10. This edge has 14, right? So I think it's the same concept. It's the same thing. So the starting is 0, or is that 13? Let me think. Oh, does it matter? I don't think it matters. All right. So here's what I'm gonna do. Max fruits ij. Right. We set this show equal to fruits I and j. All right. And then max heap dot add push. What the hell? It is push. Oh, I think I defined it wrong. I think we missed one. There you go. So push. That is going to be fruits ij, right? It's the front. And what else? What else? What else? What else? What else? This is going to be another one, which is going to be I and j. Okay. While max heap dot is empty. Oh no, I think it's just empty. Oh, if it's not empty, we're gonna just go to the end. I think the first time we hit there, that should be fine, right? Okay, max heap dot empty, and I think we need to get it out. So can we go const auto? No, I think I just do auto. Right, fruit current I, current j, max heap dot top, and then max heap dot pop. Not sure. Decomposes into two, but only one is provided. I actually don't know how to do this. How to decompose? How to decompose this? That is not what I want. Oh, I see. Okay. So basically this has to be position. Is it auto? Yeah. So now we say auto current I, current j equal to position. Alright. So now we have fruit, current fruit. Okay, current fruit. If current fruit, oh actually no, we have to do this as well. If current fruit is not equal to max fruit ci, cj, we'll continue. Alright, continue, so this is a wrong one. If it's equal, that's fine, we take it. And then we'll go through all the directions. So we say for const auto direction. So di dj of dirs. Right. So we have di dj. It's the next step. Next I equal to current I plus di. Next j equal to current j plus dj. Good. So I have next I, next j if large equal to 0 and next I smaller than n, and next j large equal to 0 and next j smaller than n. So this is within range. And there's also a limit. Limit. Alright, so we can say int row limit, int column limit. Okay. So it's blah 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 blah. So this, and then row limit has the smaller than row limit. And this has to smaller than, and j is not going to be larger than column limit, because we hold on to those two. Okay, so this is what we can do. And what do we say? We say the next fruit should be current fruit plus the next fruit. So fruits ni and j, this is the next fruit. If next fruit is larger than max fruits ni and j, that's the case. So we go max fruits ni and j shall equal to next fruit, and we'll go max heap dot push next fruit ni and j. Okay, so yeah, we do that, blah 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 blah, which is fine, everything is fine. So we push this in. This is the big one next we can go to. And yep, that's about it. But what we need to do here is, if current I is equal to n minus 1 and current j is equal to n minus 1, then we just return current fruit. That is the largest. Huh. Alright, we just break it then. Now I return max fruits in n-1, n-1. Okay, that's Dijkstra. So we have a result equal to 0, and we say go through all the cells for child 0. And equal to fruits of size. Okay, s equal to 0, s1 and I plus rest plus equal to fruits I. Okay, that's that. And then when I return res plus actually I think let's make it more explicit. Child 1 f extra, so child 1 in my case is n-1 0, which is the bottom left. Okay, and this is fruits, nothing changes. Holy smokes, we need to mark it as 0. Although technically it doesn't really matter, does it? Mark it as 0. Well, let me see if it matters. Because you're doing maximum, so I think it matters. Oh, hold a second. You're doing maximum. You're doing minimum is fine, but you're doing maximum. But you have the directions settled. So once you add 1, you're always moving right. So there's no chance for you to revisit the ones in the left. So I guess it's fine. But I do have to set these to 0 just in case. There's no J. Alright, so this is fine. Fruits. This is direction. This is actually very important. Directions. So directions for this is going to be, since it's bottom left, so it's going to be this. This is moving to the right. This is diagonal. And -1 0, -1 1, right? -1 1 0 1 and 1 1. Yeah. Okay, so row limit. So it has to be. It cannot be bigger. Okay, let's change this into larger equal to. So make it a bit easier. Row limit. And this has to be column limit. Okay, so row limit is going to be n-2. That's a row limit. Column limit is just going to be 0. There's no column limit. Alright, and then we can say child 2 fruit is Dijkstra. This is going to be 0. n-1, which is the top right corner. And this is going to be fruits as well. So this is going to be, hold a second. Alright, so we're gonna go down, which is 1, 0. Okay. Always go down. So it'll be 1 minus 1. Always down. It'll be 1, 1. Actually, let's do 1 minus 1 here. Let's do 1, 1 here. Row limit n minus 1. It has to be smaller or equal to n minus 1. Column limit is n minus 2. It has to be larger than n minus 2. Right, it'd be 1, 0. No, 1, 0, 1 minus 1, and a 1, 1. So, undefined n. Oh my goodness. Oh, okay. Huh. Yeah, it's a L value cannot bind. Yeah, it's a reference. So I either copy it. I don't like it. All right, let's do it differently. Let's do child 1. And that is a dir's 1. Okay, and then we can do here dir's 1 and dir's 2. I'll just call f1, f2 as well. F1, f2. Might as well call this f0. Right, f0. So now we're going to return f1 plus f2 plus f3. We have f0. Alright, let's try to see if it works. Maybe I don't. Doesn't work. I am just going to copy and paste and then call it a day. Oh my goodness, that is bad. Even the second one doesn't work. How in the world the second one doesn't work? I don't know. I honestly no idea. What if we just return CF? Should not reach here. Will it work? That was even worse. What the hell? Yeah, we are here, right? And this is 0. So this position is 0. Huh. Maybe I don't do this. Maybe I wait until it's complete. Yeah, I should wait until it's complete. Oh, Jesus. Jesus! Okay, so I'm at this position. That's good. Fruit should be 1. Right? I put it out. It is equal. So I don't continue. So I check my next directions. So I can go up. Now I can go down, which is nothing. I can go diagonal, which is nothing. And I can go right. So I'll go right. And then next will be 1. And 1 is larger than the max fruit. Yeah? 1 is larger than the max fruit. And then max fruit, this shall equal to 1. Right? And then it will push this in. I'll push this, the next fruit is 1, this in. And then here go next one coming out. It is equal. And then you're trying to go different direction, but all of them are bad. So you don't, so you get out. So you max fruit. This should give you 1. Right? And you go the other one, it should give you 1. So you got 4. That is bonkers, man. Okay, I don't know why it does not work. I think it's worth investigating. Right? I think it's worth investigating. So I'm breaking my own rule. Yeah, but it's necessary. Actually, I'm getting a little bit more invested in this problem, so I guess it's fine. I will indulge myself. This is fruits. This is wrong. This should be vector of int and int. Okay. And this one shall be max. This, and then we go fruits. I think it should be this. Oh, what the hell? Okay. Today is what? 7. 7. Okay. Let's see, where do we stand? Yeah, we stand here. We do this. All right, let's debug this stuff. Okay, directions, fruits. We know what fruits are. Directions 0, 1, 1, 1. We're always going right. That's correct. Max fruit. Yep, max fruit is fine. Max heap. I don't know, how can I see max heap? Oh my goodness, this is definitely not easy to see. Whatever. Let's just go through this. So max heap will push in. Alright, so CF, and let's see, what's CF? Where's our CF and CICJ? I don't see the CICJ though. What? Oh, it didn't even come out yet. Huh? It doesn't get recognized here. So I don't know what CI is. I don't know what CJ is. Dude. This is pretty bad. Like, I don't know what this is. Yeah, this is not gonna work. Maybe I can use this in some other ways, but for now, I have to be more. So we can say p max heap.top cf p.first ci p.second.first cj p.second.second. Unfortunately, this is the only way I think I can make them visible. Yep, that's the only way. So we are at 1-0. That's true. So max ij, max fruit ij. So I can put this one out. Oh, jeez. I think we should get this out as well. So CF is 1, max ij is 1-0. Right? It's good. So now we go to DI/DJ. Okay. So DI/DJ. So NI is 1-1. Right? We go to 1-1. Now 1-1 should already be 0. Oh, hold a second. What about F0? We'll worry about this later. So 1-1 is good. 1-1 is not good. How did you figure? 1-1 is not good. Is that column limit? Column limit will be 0. NI. Row limit. What's row limit? Both are 0. Oh, F4. I think I know what goes wrong. Ni should be larger equal to row limit and smaller than n. Yeah, I think that was the reason. Alright, so one of them is right, the other one is still wrong, which is okay, we can debug. But it's really late. Well, I'll leave the debugging for tomorrow. I still think this is the right approach, but who knows, maybe this approach is not right. Very likely, very likely. But hey, I haven't given up yet. Ugh. I have not given up. Yeah, maybe just, let's just do this. We'll check it. We'll check. All right, coming. Okay, let's see what goes wrong. So the path should be straight to the right. Should be straight to the right. Okay, current root is 13. That's good. Row limit is 2. 0, 1, 2. Column limit is 0. How is column limit 0? Column limit shall be n minus 2. Oh wait, hold on. Column limit for this one is 0. Yeah, that's correct. Ooh, this is a row limit? I think this is where it go wrong. Row limit should be 0. Alright, let's change this parameter and try it again. Voila! Both are good. Alright, so guess it doesn't work. How? Did we do Dijkstra wrong? This requires some analysis. I don't quite understand. It shouldn't be hard to figure out. This is 6 by 6. We can analyze this. But you probably don't even need Dijkstra. I think you just pick the bigger of the two. Why do you need Dijkstra? Right? Just pick the bigger of the two. I don't think you need Dijkstra, man. So, don't do Dijkstra. We say get max fruits. Alright, get max fruit roll. No, ij. This is the starting point. This can tell us, and what we need to do is just do the yeah, I feel like we don't need Dijkstra. That should be it, right? Okay, if I is equal to a minus 1, is child 1, alright, greedily going through the bottom two rows. I think this is the only thing we need. just the maximum. Oh, that is not right. That is not right. Fruits. Oh, let's put the J in there. So ij is the first one we have to take. And then it's just the larger of the two. So here is going to be 1. J is a 0. In fact, I don't think I need J. Yeah, that's fine. Just put it in there. So k equal to 1, k smaller than k plus plus. So it should be maximum of fruits I k fruits I minus 1 k. Right? You just pick the bigger of the two, and then that's it. Else, this will always be true, so I don't have to do it again. Right, 2 columns. Alright, fruits k, I, in this case, I is gonna be 0. No, I think it's a J. Right, J, and fruits k, J minus 1, the right 2 columns. So instead of these, I say in type 1, get max fruits. That's a minus 1, 0, fruits. Alright, let's give this a shot. Alright, try it. That does not make any sense. What? Oh, you cannot get the last one. Before the last one. My bad. Before the last one. Oh. What do you mean Dijkstra is correct? Huh. Greedy doesn't work? I do not know. I do not know. DP. Need to debug my previous solution. I'm actually curious. Why it does not work. I don't know why. Wait, hold on. That's fine. Let's just remove it. Like, what else can you get? You get the maximum of these two, and you can go. We have to play around with this and to understand. I'm curious. I'm curious right now. Like, how does it not work? If we can get a even smaller one, that would be helpful, but I'm not sure. Okay, let's do some computation. Let me get my calculator out. Alright, so diagonal. This is the diagonal. Okay. 1, 2, 3, 4, 5 steps. So 4 plus 4. We are missing 4, but that shouldn't be the reason. Four plus 4 plus 15, 17. 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 2, and then 16. Okay, 58. So F0 is 58. So if I here F1, 16, 17, 6, 14, 7. I got 60. F2, 14, 16, 9, 7, 14. I got 60. Yep, that's 178. How'd you get 182? Oh, wait, hold a second. I need 5, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Ooh, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Huh? How? I see. You can deviate. So 1, 2, 3. 1, 2, 3, 4, 5. But then I can get 11. Which is 5 more than the current. I can get a 183. Wait, hold on. 1 step. 2, 3. Oh, but then I get 1 less. 4, 5. So I think Dijkstra will still work, except we don't set the rules. We just need to know, at a certain position, given these is that possible? How do you know how many steps are left? Like, why in this one we can do it? Right? Well, in this one we can do it because I have how many steps left? So the difference between this and this is that now we're still moving right. Every step we're moving right. Every step we're moving right is just moving down. Like if you're here, you want to have 2 steps left. You need to move down 3 steps. But if you're here, you have 3 steps left and a 3 step down. So basically we can still reach. So I can even go here, right? And then here. It's actually no. 1, 2, 3, 4. 1, 2, 3, 4, 5. That doesn't work. But in here it works. Why does it work? Because you need two 2 steps down, 3 steps. So no, you have 3 steps left, right? 3 steps left, and it's possible because every step is going right. So you also have 3 steps. So like you're here, like 1, 2, 3. As long as the number of steps go like if you're deviating, right? If you're deviating, as long as the amount of deviation is smaller or equal to the amount that needs to go, then that is a good thing. Which means in that case, it is a good thing. So I think what we need to do is revive the Dijkstra, but don't do this. I think this one's definitely not right. Right, this one's definitely not right. But I think Dijkstra might still work. Dude, I think Dijkstra might still work. I just need to change it. Change the condition. Like, we don't need the limit, hard limit. Right, that's not what we need. What we need is not a hard limit, but a new way of determining whether a cell is accessible or not. So we just need to know whether this one is accessible or not. Alright, let me just go 0. And then this has to be 0 as well. But we need another check. Right, whether this position, so we need to check whether it's possible. Whether it is possible to reach n-1 in the remaining n minus so how many steps? Minus like I'm at this, right? If I'm at ni, I need to reach nj steps. Depends. For child 1 or minus ni steps for child 2. Okay. How do I know if it's child 1 or child 2? Well, if I is equal to n minus 1, this is child 1, and right, I is n minus 1, and n minus 1 minus nj is the remaining steps. You only have this much of steps, which means your ni should not be, so your ni should be smaller or equal to this. what is this thing? The number of steps need to come down, right? So it's n minus 1 minus ni, right? Is smaller or equal to, yeah, minus nj. This is the hard limit. We have to move right every step. So we can venture up. As long as we have enough room. Yeah, so if this is possible, okay, or I is equal to 0 and something smaller equal to something. So this is, we're always moving down, right? So n minus 1 minus ni. This is n on the left, and this should be n minus 1 minus nj. So if that's the case, then we can do. Alright, so if this was not right, I guess it just doesn't work. Alright, try this. Would they still be able to meet? They still be able to meet. I think it's probably still not right. Because now they can meet each other. I'm not sure. I'll give it a run. If it still fails, then yeah, we know this doesn't work. Okay. Okay, so it works, but it times out. That makes me happy. That makes me happy. Yeah, it times out. I am surprised that it will time out. But, anyway. Well, the logic is sound, but it times out, TLE. It's alright, it just means we have to check the solution. Alright, albeit good struggle. Alright, good struggle.